Let us begin the presentation. Explaining the proof that carbon dioxide causes global warming. After this presentation you will hopefully understand exactly how this proof works. Note that popular literature often uses climate model simulations to conclude that global warming must be caused by man-made emissions of carbon dioxide. That is not a stringent, scientific proof, and will not be discussed here. Next. The proof presented here was published in a paper by Stips in Nature. There is a reference to the Stips paper at the end of this presentation. Stips basically compares carbon dioxide measurements to global temperature observations, and uses a novel statistical method by Liang to estimate the information flow between the two data sets. Next. On the left, we see the carbon dioxide measurements. On the right, we have the mean global temperature. There is a strong common signal in both data sets, they both increase with time. Notice also that the carbon dioxide measurements have less noise than the global temperature observations. This is important for the Liang analysis. So, Liang estimates that information is flowing from the carbon dioxide dataset to the global temperature. No information flows the other way. So, since information only flows from carbon dioxide to global temperature, the carbon dioxide must cause global warming. The next slide examines the Liang method in more detail, although the mathematics are pushed to the end of this presentation. Next. Liang assumes that the information transfer is linear, which means that the signal and noise is transferred together. The receiving dataset cannot distinguish noise from signal, so the receiving dataset must have more noise than the sending dataset. Information must therefore flow from the dataset with little noise to the dataset with a lot of noise when the signal is strong. Next. The linear information transfer assumption is critical to the Liang method. Liang claims that this assumption holds in general, which is a fair statement. How is it even possible to only transfer the signal and not the noise? Stips then claims that the assumption also holds for the information flow between carbon dioxide and the global temperature. And why should it not? So, let us complement our intuition with two examples. Next. In this example we study the information flow between global mean sea level, on the left, and the mean global temperature, on the right. The datasets share a strong common signal, they both increase in time. The mean sea level has less noise than the global temperature, and so the Liang method estimates that information is flowing from the sea level to the global temperature. According to the method, the global mean sea level is causing global warming, which is not correct. So, we know that the rising global temperature is causing the rise in the global mean sea level. The Liang method should not be applied in this case since the information transfer is not linear. Instead, information passes through a low-pass filter from the global temperature to the mean global sea level, so that only the low-frequency signal, and not the high-frequency noise, is passed from the global temperature to the global sea level. Next we study an example with simulated soil temperature, on the left, and simulated surface temperature, on the right. We know that the surface temperature transfers heat to the soil using the heat equation. We observe that both datasets have a strong common signal, and that the soil temperature has less noise than the surface temperature. The Liang method estimates that information is flowing from the soil to the surface, which we know is not correct. So, again, the Liang method should not be applied since the linear information transfer assumption is not valid. Information is rather transferred from the surface to the soil through a low-pass filter, which only passes on the low-frequency signal, and not the high-frequency noise. Let us finally use mathematics to show that Liang will estimate that the information flow will flow from the dataset with little noise to the dataset with a lot of noise when the signal is strong. Next. Equation 1 shows the expression derived by Liang to estimate the information flow between dataset X and Y. The coefficients are also listed in equation array 2, so that you can apply this method to your own data. Next, let us study datasets X and Y with a common signal S. Dataset X has the signal S plus some noise given by sigma X. Dataset Y has the same signal but with a different noise given by sigma Y. The signal has autocorrelation A, which just means that it is smooth. The Liang coefficients are then given by equations 4. Next, let us apply these coefficients to the Liang expression for information flow. We are interested in the limit where the signal is much stronger than the noise. The information flow is then proportional to the autocorrelation or smoothness. We see from equations 5 that if the X dataset has little noise, so that sigma X is small compared to sigma Y, we see that the information flow from X to Y is equal to the autocorrelation, while the flow the opposite way is 0. In other words, Liang estimates that information flows from the dataset with little noise to the dataset with a lot of noise. Next, if we take a limit where the signal is much weaker than the noise, the information flow is always 0, as shown in equation 6. Next, finally, here are the references to the papers by Stips and Liang. I recommend the paper by Liang if you are interested in marginal distributions, divergence and entropy. The Liang method is not the only scientific method available to determine the causality in this problem. Share, and I will consider making a new video that applies the standard method proposed by Clive Granger, which earned him a Nobel Prize. Thank you for your time, and stay safe. Normal end of presentation.